My name is Scott Wakely. I'm the director of the Enrico Fermi Institute, and it's my job to welcome you here to the 87th Arthur Holly Compton Lecture Series. So the lectures are named after Arthur Holly Compton, who was a very distinguished U.S. Scientist who worked here at the university in the physics department for about 22 years. He's a Nobel laureate. I mean, everybody's heard of Compton. During World War II, he was largely responsible for putting together a team of extremely distinguished scientists to come to Chicago and work on the war effort in the nuclear program. And that team included people like Enrico Fermi, Heller, Urey, Anderson, Gebhard Meyer. So really an amazing crew. And they were brought here to work on the nuclear program. And after the war, they, or at least a good fraction of that group, formed the core of two new research institutes here at Chicago. One of which is the James Franck Institute, and the other is the Enrico Fermi Institute. And those institutes were basically built here to the north. The whole city block of infrastructure, there was labs and a particle accelerator. And that infrastructure and that team brought together the best and the brightest scientists from across the country and the world. And within the institute, in about the 70s, John Simpson, who was the director of the Institute, had the idea that we should provide a platform for the best and the brightest of our young students and postdoctoral students to share their excitement about their research. And that was how the lecture series was born. It was originally supported through a generous donation by a friend of Compton's, whose name I always have to check, John W. Watzek was his name. And that's what kicked it off. And in recent years, the lectures are supported by the Institute and by generous donations from people who have come to the lectures. So we've tried to make it easier for people to donate to the series. And so if you are inclined to do so, you can visit the efi.uchicago webpage, and there's a link there. And if it's just in time for tax season, you can donate up to $100,000. Now let me introduce this season's lecturer. It's Andrew Mastbaum, Andy. He is an experimental particle physicist who specializes in neutrinos. This should be a real treat. We haven't had a neutrino expert do the series in many years, over 20 years, I think. And there's a lot that's happened in that time. So I'm really tickled that he said yes. Andy got his PhD at Penn in 2016, and he came to Chicago that year as a Granger Fellow. Granger Fellow is a distinguished fellowship in the physics department that's reserved for the best of our young experimental students. So we were very happy to have him here in Chicago, and very happy to have him as our Compton lecturer. So the topic of his series is the physics of neutrinos, progress, and puzzles. And I hope you will come and pay attention to Andy and ask him many, many questions. And I will see you guys at the end of the series for our traditional brunch. So please welcome Andy. Thank you. Godspeed.
There, you hear me okay? Great. Well, I'm honored to be here, and I'm thrilled that you all chose to spend your Saturday morning out here learning about neutrinos with me. So let's get started. So when you look at the sun, not directly at the sun, because that's dangerous, as you may know, what you're seeing are photons, particles of light, which we symbolize with Greek letter gamma. What you might not know is that there are a whole bunch of other subatomic particles coming at you from the sun, called neutrinos, which are symbolized by the Greek letter nu There's tens of trillions of neutrinos going through you every second coming from the sun. And for a long time, nobody knew how the sun worked. Nobody knew what made the sun shine. And certainly we didn't know anything about these neutrinos. But today, we have a pretty detailed model of what happens inside the sun. We know that there are nuclear fusion reactions happening deep within the core of the sun that produce these photons and these neutrinos. And the photons, when they come out, they bounce off of electrons inside the sun. And they spend about 10,000 years kind of bouncing back and forth throughout the sun as they slowly make their way out before they finally get to the outer surface, the photosphere, where they then stream their way to Earth to warm your lovely faces. But by the time they get out, they actually don't carry that much information about what happens inside the sun. So we can't really learn about what's happening in the core of the sun by looking at these photons. The neutrinos, on the other hand, they hardly interact with matter at all. They pass straight through the sun, they'll make their way to Earth. Some of them will come in your head and out your feet, down through the Earth, all the way through and then into outer space forever. But if we can detect these neutrinos, which is difficult but possible, and we'll talk a lot more about that, we can actually kind of see inside the sun. We can use these neutrinos to understand what's happening in these fusion reactions and understand what's happening that makes the sun shine. And so that is really how we know what we know about the sun and other stars today is largely through the study of these neutrinos. If we step back even further and think about the whole universe. If we look around the universe today, we see a whole bunch of matter. There's a whole bunch of stuff. There's us, there's planets, there's galaxies and everything. And it's relatively homogeneous, meaning it's uniform throughout, and isotropic, that looks the same in all directions. And in particular, it's full of matter and not antimatter. If you're not familiar with antimatter, that's okay. It's not as sinister as Dan Brown novels might lead you to believe. Here's some matter. This is an atom with a proton and neutron in the nucleus. The proton is positively charged. Flying around it is a negatively charged electron. Here's some antimatter. This is an anti-atom in the nucleus. It has an antiproton and an anti-neutron. They have the opposite charges but the same masses. And flying around it is the anti-electron, which we call a positron. It's positively charged. So they're really not, there's nothing weird about this. It's just different. It's just kind of the same particles but all opposite charges. And if we drill down even further, we know now that the stuff in the nucleus is made of even smaller bits called quarks. And that is the smallest thing we know about. That's as far as we know, the smallest you get. Okay, so we have this matter and antimatter. We have a universe full of matter, but not so much antimatter. Now, the universe that we see today is expanding. So if you play the clock backwards, you have a universe that's getting smaller and smaller, and hotter and more dense. Until you eventually reach a point where you have the entire energy content of the universe compressed into a tiny space such that the laws of physics just break down. And we no longer have a physical description of what happens. This is like the singularity of the Big Bang. But if you think just after that, we have this extremely hot, dense plasma in the universe. There's a ton of energy. And we know from Einstein that, his favorite equation, that E equals mc squared, that energy and mass are equivalent. And so when we have this hot, dense ball of energy, we can create matter. In particular, we can do what's called pair production, where we take some energy and create particle-antiparticle pairs. For example, we can create an electron and a positron together. And there's an inverse reaction called pair annihilation. Pair annihilation, where matter and antimatter come together and annihilate each other and turn back into energy. All right, so in this early universe, we're boiling off a bunch of particle-antiparticle pairs that eventually find each other, annihilate, and we just have energy. It's all in equilibrium. And so if we play that picture forward, what we would expect is that basically all the matter and antimatter, which is created in equal parts, annihilates each other, and we end up with a universe that's full of nothing. Well, nothing but energy, just photons flying around, and not all these galaxies and people that we have. But indeed, what we see is not nothing but everything. All right, so it's a bit of a mystery how we end up in this situation. And so this is still sort of an open question, how we create this matter-antimatter asymmetry that leads to the existence of the universe. Our best theory right now involves neutrinos. That when you produce neutrino-antineutrino pairs out of this vacuum, they go off and interact slightly differently, so that over time you build up an excess of neutrinos relative to antineutrinos. which then is converted into an excess of atoms over anti-atoms. And so when all the cancellation is done, you end up with a little bit of extra matter that turns into everything you see, a process called leptogenesis. We'll come back and talk more about that, of course, later in the series. These neutrinos, they're sort of everywhere, right? They can teach us about stars and what's happening inside them, other astrophysical systems. They may hold some keys to understanding the history and evolution of the universe. A little closer to home, remember they're produced in nuclear reactions, and they just go through matter, like they don't even care. So actually they can be quite useful as a test to see if there's any, if you're trying to detect a nuclear reactor or a nuclear test. That's a very practical application where you can use neutrinos. But also these are just some of the fundamental building blocks of matter. And so it behooves us to try to understand them. You know, we've always been on a quest to understand what we're made of at the smallest levels. And so understanding neutrinos, you know, for their own sake, is an important piece of that puzzle. So with that, I welcome you all to the 87th Compton lecture series titled Physics of Neutrinos, Progress and Puzzles. And here I just outline a few goals that I have, you know, both for today and for the whole lecture series. So I hope you leave with an understanding of what neutrinos are and what they mean within our, you know, the context of our understanding of physical interactions. We'll go through some of the major experimental efforts and what some of the open questions are in neutrino and particle physics. You know, so you'll know what keeps neutrino physicists up at night. And I want to, you know, really highlight this dichotomy that there's still a lot we don't understand about neutrinos. And so they're objects of study in their own right, but in the meantime, we know enough about them to use them as tools to understand other systems, like seeing inside of stars. I think that's a really neat thing. So to get there, here's a rough agenda of you know, what we're talking about each week. So we start today with some of the history of how neutrinos were originally discovered and some of their main properties that we know about, and then we'll kind of touch on some of the major research topics that are interesting to people today, and there's a lot of effort within the Enrico Fermi Institute. Subject to change depending on how things go, and I certainly welcome people's feedback. If you want to come talk to me after the lecture or send me an email, and I'm happy to hear your people's thoughts. So with that, let's go ahead and get started with the discovery of neutrinos. So the story begins around the turn of the 20th century, when people are studying radiation. So by this point, people had sort of categorized radiation, which is, you know, nuclear decays, when nuclei spontaneously fall apart in various ways. And they had categorized them into three basic types, somewhat uncreatively named alpha, beta, and gamma decay. The alpha decay, that's when a nucleus, as we now know, spits out a so-called alpha particle, which is 2 neutrons and 2 protons. It's a helium nucleus. And so it loses 4 units of mass and 2 units. It loses 2 protons, but loses 2 units of the atomic number. And so it gets lighter and moves down the periodic table by 2 units. In a beta decay, the nucleus spits out an electron, which they call a beta. Know what it was at that point. And so the electron being negatively charged means you have to change the charge of the nucleus. So what we understand is happening now is that a neutron turns into a proton within the nucleus. So you go up the periodic table by 1 unit. And then finally, we have gamma decay, where the nucleus, it doesn't change mass or charge. It's just in some higher energy configuration and relaxes by spitting out high energy photons. So just to show you, beta decay is real and everywhere. I have here, this is a chunk of strontium-90, which is a radioactive isotope, and here I have a Geiger counter, which is a radiation detector. So it clicks every time a charged particle goes through it, like the electron or the beta decay. So there you have it. Beta decay is happening, you know, right in this room. So this was great. This was a major discovery, but soon there was trouble. So around the 1920s, some work pioneered by James Chadwick, they were interested in studying the energy or the velocity of the electrons that were coming out of these beta decays. And what you would expect is the nucleus is so heavy and the electron is so light, it's sort of like shooting a ping pong ball out of a cannon. They share the momentum, they have opposite and equal momentum, but the kinetic energy is very different. The cannon moves very slowly, the ping pong ball moves very quickly. And so what you would expect is, if you take the difference in energy between this final nucleus and the initial nucleus, all of that energy should turn into the velocity of this electron. So you can calculate exactly what that number is for any given nucleus. And so if you measure the velocity of the electron, what you expect is to get that one value all the time. So that's the expectation. They use a device similar to this to measure the energy of these electrons coming out. And what they find is this instead. This continuous spectrum where the electron has a random energy, which is always less than the value that they expected. So in this case, we have some problems here, right? It looks like energy is just disappearing. And so this was a major problem people were very concerned about, because it was perhaps a hint that here we thought for a very long time, even millennia, that energy is conserved always. Energy can change forms but never be created or destroyed. And here we have these nuclear decays where energy just poof, it just vanishes. Right, so this had people very worried. There were certainly prominent physicists who were just ready to give up on energy conservation and say that it was only on average and that any particular decay didn't have to conserve energy. People were very careful. They were all scratching their heads at a conference in 1930 when a letter arrives from physicist Wolfgang Pauli. It's in German, so I will translate. He says, "Dear radioactive ladies and gentlemen," to which the ladies and gentlemen are like, "You're calling radioactive. I have hit upon a desperate remedy. There could exist electrically neutral particles that would be produced in the beta decay along with the electron. The continuous beta spectrum would then make sense. In addition to the electron, a neutron is emitted." Here he doesn't mean the neutron that we know of in the nucleus. It hadn't actually been discovered. It wouldn't be for another 2 years. So he means a neutrino, but he calls it a neutron. So the neutron is emitted such that the sum of the energies of the neutron and electron is constant. He's a bit concerned about this, though. He says, "I do not dare to publish anything." And in fact, he doesn't even show up to the meeting. "Unfortunately, I cannot personally appear since I am indispensable here in Zurich for a ball." I mean, you can't get excuses like this anymore. Like, man, I couldn't get away with that. But Pauli had done a bad thing, and he knew it. Right? He says, "I've done a terrible thing today by proposing a particle that cannot be detected. It is something no theorist should ever do." So what he is proposing is energy conservation is fine. You can hold on to that like sacred tenet of physics. Instead, there is some invisible particle, some invisible participant in beta decays that is taking away some energy and carrying up. So he invents a new decay product, which is concocted specifically to not be detected, right? Which is making people very uneasy, because that's really kind of the whole thing with science is you want a theory you can go out and test, and this is deliberately crafted so you can't. So people are okay, a little unsure about this. In 1934, Enrico Fermi comes along, after whom our fine institute is named, due to his time he spent here at Chicago. And he works out a new quantum mechanical theory of beta decay. So he's working out a theory of how this decay proceeds, including this new neutral particle which can cart off some of the energy. So we have within the nucleus now a neutron turning into a proton, emitting an electron, and this new neutral particle that Pauli had invented. So this is a really beautiful theory, and in fact he invents the whole mathematical framework that we still use today. Details are not important, but basically he writes down some rules that you can calculate the rate of how often this happens in terms of some constant times this factor m, which is the probability to go from whatever initial state you start with to whatever final state you end up with, times this factor rho, which takes care of the conservation of energy and momentum. And so in this picture, this interaction happens at exactly one point in space-time. You have a neutron coming in, and poof, it instantly turns into proton, electron, and neutrino. And so using this theory that he developed, he was able to calculate the energy spectra of electrons coming out of beta decay, and found these continuous spectra, just like what was observed, right? So this is a great success. We now have a theoretical description that matches what was seen in the experiments. Still at this point, theoretical, right? These particles are still undetectable. So people were very interested, of course, to see if you, could ever find one of these things. So just a few months later, really, Hans Bethe and Rudolf Peierls decided they're going to calculate the neutrino cross-section, the probability of interacting with matter. So we have beta decay, which Fermi tells us about. And his model gives us the ability to kind of flip around the arrows in that diagram. So we can use the same equation to figure out what the rate of the inverse beta decay is, which is when we take a neutrino, fire it at some matter, it hits a proton, turning it into a neutron, and now a positron comes out, the electron in the particle. So Bethe and Peierls, both very prominent physicists. Bethe basically invented nuclear physics. They decided to do this calculation. And so they say, possibility of creating neutrinos necessarily implies the existence of annihilation processes, the most interesting of which, amongst them, is the following. A neutrino hits a nucleus, and a positive or negative electron is created, while the neutrino disappears, and the charge of the nucleus changes by 1. That's exactly this inverse beta decay process. And it takes, assuming the energies of the electrons that are coming out of beta decays, you can calculate the probability of this happening. And they calculate that if you're going to detect one of these things, say you had like a big chunk of lead you're going to fire neutrinos at, and you want to see one run into a proton and create a positron. You would need 10 to the 16 kilometers of lead for a neutrino to interact, which is like 1,000 light years of lead. So these things really don't like to interact with matter. And so they say it is therefore absolutely impossible to observe processes of this kind with the neutrinos created at nuclear transformations. And go on, one can conclude that there is no practically possible way of observing the neutrino. This makes me very sad. They say that a neutrino is going to go through 1,000 light years of light. But we need experimentalists. We do not let the theorists get us down. We go for it anyway. And so really, the trick is to realize that this is a numbers game, and that we're looking for these interactions with matter. And the event rate is the probability of interaction, which is very small, times the number of neutrinos you have to work with. And more quantitatively, the rate of interactions is given by the number of targets, the number of protons available to hit, times the flux, which is the number of neutrinos per unit area per second you throw at it, times the cross-section, which is like its probability of interaction, times how good you are at detecting the interaction. So as an analogy, let's say you had like a big field full of bowling pins, and a bowling ball. You're going to throw your bowling ball at random and try to hit a bowling pin. Your odds are not so good, because the cross-sectional area of the bowling pins is relatively small. But if you took a dump truck full of bowling balls and let it rip, right, then you increase your chances just by having a huge number of bowling balls being fired at your target. So that's kind of the game with trying to detect neutrinos. We just need a whole lot. So I'll take a pause here to say how we would actually go about detecting these undetectable particles. So here we have the neutrino department, our elementary particle. And what we're looking for is the neutrinos are electrically neutral. They're very tricky to detect. So what we wait for is the neutrino to come in, it's invisible, and smack into a nucleus, like a proton, and some charged particles come flying out. So we hit a proton, and a positron comes flying out, the charged particle. So we're looking for kind of something coming from nothing. We fill our detector with a material like liquid scintillator, which is just a fluid that produces light when charged particles go through it. So we have a positron going through, we get a flash of light. We can then instrument our detector with a device called a photomultiplier tube, which is just a super sensitive light detector that can see single photons. So we have a neutrino come in, create a charged particle, makes a flash of light, and we detect the flash of light with our waiting photomultiplier tubes as a little electrical pulse. And therefore, we've detected neutrinos. Maybe. These interactions are very rare, and there's a lot of things out there that can try to fake you out. Things that happen a lot more often than neutrino interactions, like cosmic rays coming from the sky, or even just the natural radioactivity of the detector materials in the Earth and so on. So it is, tricky to detect these above these boundaries. Now, neutrino detectors today are incredibly sophisticated, very sensitive instruments. For example, the Snow Plus experiment up in Sudbury, Ontario. We'll talk about this in the next few lectures. Or here's the prototype for the deep underground neutrino experiment being built in CERN. Here's the Core experiment. This is underground in an underground mine, underground laboratory in Italy. This is a whole bunch of crystals that are put in a refrigerator that is so cold that it is actually the coldest square meter of the universe. Neutrino detectors originally, though, they were a bit more humble, but the same idea. So this is really like the first large-ish neutrino detector at the Los National Laboratory back in 1953. And it's exactly as I described. It's a big bucket full of liquid scintillator with a bunch of photomultiplier tubes around it. Okay, so we have our detector. Now we need a whole lot of neutrinos to throw out. So if you're at Los Alamos in 1953, these guys, they hatched a plan. They called it Project Poltergeist. And something they had very much on their minds at Los Alamos in these days are nuclear bombs, right? Nuclear testing. And so they devised an experiment. They realized that in the nuclear fission that's happening in this reaction, you're producing a lot of unstable isotopes that can undergo beta decay. And when things beta decay, they produce neutrinos. So they have a whole lot of beta decays producing a whole lot of neutrinos inside that mushroom cloud. So you'd like to put your neutrino detector like right there and catch all those neutrinos, which is not such a super place for your super sensitive detector right next to a nuclear blast. So the plan is you set off the nuclear bomb. It makes a whole lot of neutrinos. But you can't just put your detector there. So they dig a big hole, and they hang their detector from the ceiling of the hole, and when they send the signal that says, okay, fire the bomb, they drop the detector. So now it's just free-falling, because if it was actually touching anything, it would shake the snot out of it. So it's free-falling until the worst is over, and then it lands on a pile of feathers and foam rubber and springs and stuff. They're like, fine, and when the coast is clear, and they go back, look at their detector and see how many neutrinos they saw. Right? I mean, it's okay. That could work, maybe. So they got as far as actually digging the hole before their boss came along and said, okay, interesting idea, but there's actually a much better way. And that is using nuclear reactors. So, nuclear reactors 101, you take a whole bunch of fissile material, meaning some kind of isotope that's easy to break apart, like uranium-235, for example. You fire a neutron at it, and it splits apart in a process called fission. And when that splits apart, a bunch of neutrons come flying out. Maybe they hit another uranium-235, and it does its fission, and then more neutrons come flying out, and so you get a chain reaction. Every time so again, like these fission products, some of them are unstable isotopes that beta decay, so you get neutrinos coming out of this process. It's about 6 neutrinos every time you do a fission. So people had begun to understand this in the 1930s, the pioneering work of scientists like Lisa Leitner and Otto Hahn. But the first, really strong proof of concept that you could really control such a chain reaction to build a nuclear reactor was right here on the campus of UChicago, the so-called Chicago Pilot 1 in 1942. So there's a picture of this reactor, which they built underneath the stadium, and a more recent cake that looks like the reactor. Here's the team that built it. I guess outside that stadium, it's down the road. I think not in the picture, but also very influential to this process, was nuclear physicist Maria Gecker-Meyer, who's a physicist here and at the Argonne Lab. And she's actually who this auditorium, this beautiful auditorium, is named for now. So of course now we have commercial power plants where we take the excess energy produced in these fission reactions, use it to, say, heat up some water, spin some turbines, and produce electricity. Let's step back a minute to the Savannah River site, which is a Department of Energy laboratory in 1956. You have to do that with DOE labs, the typewriter test. So inside this building, there's a nuclear reactor. And those fission products coming out of that, the nuclear transformations are making tons of neutrinos. And so 2 of these Los Alamos physicists, Fred Reines and Clyde Cowan, set up their neutrino detector just down the hall from the nuclear reactor. And it's basically as I described, some simplified view, but you have some liquid scintillators and photomultiplier tubes. You put it next to the reactor. So it's hooked up here to my oscilloscope. So that when a flash of light produces an electrical pulse in the photomultiplier tubes, I'll see a little blip on my oscilloscope. So sitting there and waiting for neutrinos from the reactor to interact with protons to produce neutrons and positons. It's inverse beta decay. And the signature of this reaction is that we see a flash of light from the positron immediately. We have charged particles in the center. It's a flash of light. The neutron is neutral, so it doesn't immediately produce light. It bounces around for a little bit, and then some nucleus in the detector will capture it, putting it into a higher energy state, and then it's going to gamma decay. So it emits a higher energy photon, which then produces another flash of light by running into something in the detector. It's a bit indirect, but basically what we're looking for is flash from the positron and the neutron. Or on our oscilloscope, we see flip, positron, neutron. And so this is great because it's really hard for radioactive backgrounds, all the alpha, beta, gamma decays happening in your detector materials in the Earth and so on, to fake this due to this coincidence. So they set up shop next to the reactor and they wait. And soon enough, they see it. Right? These are the actual oscilloscope traces that they published. You can see here flip, positron, neutron. Right? So after 26 years after the proposal, this undetectable particle has been found. A few more years later, in 1995, Fred Minus got the Nobel Prize for this discovery. So, huzzah! Right? Beta decay is fine, energy conservation is okay. These new particles that everyone's so skeptical about, that Pauli had invented in Dear Radioactive, ladies and gentlemen, and Fermi came up with a theory to describe them, everyone is vindicated, right? These things are real and they're out there. So you might think in 1956, things are looking good. We needed it, we found it, all is well. Neutrinos are not going to let us off that easy. So soon after, the plot happens. So we talked about beta decay. Neutron goes to proton, electron, and this neutral neutrino. We talked about the inverse beta decay, which has now been found by Cowan and Reines. Neutrino turns a proton into a neutron. Positron comes flying out. And there's so this is a neutrino interacting with matter and making antimatter. It's making a positron. And there's a question of whether you ever have a neutrino coming in and interacting with matter to create an electron, or whether there's distinct neutrinos, one that makes antimatter and one that makes matter. So in the late 1950s, Ray Davis, who's a physicist at Brookhaven National Lab, devises an experiment to test this. And it's a little bit different than what Cowan and Reines had done. He takes this interaction that will only occur for, only produces an electron. So he's taking a neutrino from a nuclear reactor, and he has a big tank of chlorine. And he wants to see if he can convert a neutron in the chlorine into a proton, which is turned into argon, and an electron comes out. And this experiment doesn't actually detect the electron. He just lets this thing sit there for a while and then counts how many argons he has. It's a tricky experiment to do, but he does it, and here's his paper titled Attempt to Detect the Antineutrinos from a Nuclear Reactor by the Chlorine-37 goes to Argon-37 reaction. So if you didn't catch it's a little bit loaded, the attempt there, he did not detect this process. So this is evidence that we now have different neutrinos, one that interacts with matter to produce matter, and one that interacts with matter to produce antimatter. So these are so-called antineutrinos. So the Cowan and Reines neutrino is really an antineutrino. The one that interacts with a proton produces a positron. And we have regular type neutrinos that interact with a neutron to produce an electron. The important thing is that these are a distinct particle and antiparticle. Just like the electron and the positron are a particle and antiparticle. Now we have a neutrino and an antineutrino. So originally, in 1930, we needed one neutral thing, and now we have ended up with two somehow. So this seems like we're going the wrong way. But it gets worse. So far, we've only talked about interactions that involve electrons. And up to the 30s or so, that's all we know. We have protons and neutrons that are in the nucleus, and electrons that fly around. And that is the fundamental particles. Well, in the 30s and 40s, people were really into going up on mountaintops and studying cosmic rays. The cosmic rays are, you have some high energy particle from space, like a proton comes flying into space, wherever it comes from, smacks into something in the upper atmosphere and produces a spray of particles. And so people set up detectors to look at these particles that were coming down and found all kinds of stuff that no one had ever seen before. Stuff that wasn't nuclei weren't made of. It was something beyond protons, neutrons, and electrons. So one important one, in 1937, is the muon. The muon is just like an electron, but super heavy, which is like a really, really heavy cousin of the electron. And by studying what the interactions of these muons and what they did, they went through these detectors, they found that these muons, which are like really heavy electrons, can decay, just like a nucleus will decay. This will decay into an electron and some energy that's just missing. A few years later, in 1947, another new particle called the pion is discovered. And the pion decays into a muon, also with some missing energy. And so people wonder, we now have these other decays with these particles from the sky that are also, energy conservation seems to be broken. It would be economical if it was neutrinos coming out of these interactions. There's a question, now that we have these muons, which are like electrons, is this the same neutrino? Or do we have, again, different kinds of neutrinos? One of which will interact with electrons, and one of which will interact to produce muons. So people wanted to go out and study this, and try to see if they could find whether there was a difference. But again, it's a numbers game. You need a whole lot of these neutrinos to study them, and you don't get a whole lot by waiting for one to come from cosmic rays. So how do we get a whole lot of these muon type neutrinos? You want electron neutrinos, you go to a nuclear reactor, you set up a nuclear bomb, maybe not such a good idea. Muon neutrinos, where are we going to get those? We only know how to get them from space. So the idea is you make your own cosmic rays. So these pions, remember, will decay into a muon and possibly a neutrino, let's say it is. And so I turn my cosmic ray outside here, proton or whatever coming in, some atmosphere stuff. You get a bunch of pions decay into muons, and neutrinos. So in 1962, these fellows here, Leon Lederman, Ellen Schwartz, Jack Steinberger, devised a plan to have some laboratory-grown cosmic rays. They take a proton beam from a particle accelerator at Brookhaven National Lab. Use that as your primary cosmic rays. You replace the atmosphere stuff with a target. And so you hit a bunch of protons into your target and you get the same thing, just like what you have in the upper atmosphere. So you do that, you put a neutrino detector down there and wait for some neutrinos. Some additional complications, like you don't want all these muons going through, so you put a bit of a shield. So as a kind of a fun side story, they actually took a used battleship and built a 40-foot thick stainless steel wall to shield out all the other stuff to make sure only the neutrinos made it through. But you'll notice also, like, we're wasting so many neutrinos here, they're just going every which way. Right? So the next step is to put a magnet here, and these charged pions, these charged particles will be deflected in the magnetic field, so you can focus them down, point them at your neutrinos. Right, so this is the game to get a whole lot of neutrinos from cosmic rays, when you don't get a whole lot of neutrinos from cosmic rays. And so this is the plan, and what you do is you set up your neutrino detector and you wait to see if you have an interaction that produces a muon, or interactions that produce an electron, or both, or something else. So in 1962, they set up this experiment. Title paper a little small, observation of high-energy neutrino reactions in the existence of two kinds of neutrinos. What they found is that the neutrinos that were coming from pions never produce electrons, they only produce muons. So the neutrinos that are produced in association with a muon go on to only produce a muon. It's like they know what they came from. So this is evidence that we now have two distinct types of neutrinos, one that interacts to produce electrons, and another one that interacts to produce muons, these new heavy elements. Here's looking good, and next to these are the tracks left behind by the muons going through the detector. So this was a huge deal. 1988 Nobel Prize for Lederman, Schwartz, and Steinberger. And so again, we have started with using one neutrino to conserve energy, and now we're up to 4. Right? This is getting out of hand. But then, a few years later, so in 1975, there's so-called tau lepton gets discovered. We have the electrons, we have the muon, which is like a much heavier electron, and there's tau, which is like a ridiculously heavy electron. And so people ask, okay, is this Does this thing want its own neutrino too? So we have electron type neutrinos called nu-E that interacts with matter to produce electrons, and muon type interacts with matter to produce muons, and we have now tau type of neutrino that will interact with matter to produce these new tau particles. This is a really difficult experiment to do because the tau particles are extremely heavy, they're extremely short-lived. They like to decay into other particles immediately. So they built a detector called Donut out at Fermilab, just an hour west of here, to try to detect these. And in the year 2000, so actually not all that long ago, based on seeing just 4 tau neutrino interactions, they conclude that indeed the tau gets its own neutrino. And now we have new electron type neutrinos, muon type neutrinos, tau type neutrinos, and 3 anti-neutrinos to go with them. So we started with 1, we have 6. Proliferation of neutrinos. So let's try to sum that up a little bit. So let's pull it all together. All right, so far we have electron, muon, and tau, called them a nu-E, nu-mu, and nu-tau. 3 antiparticles that go along with them, and they all do different things. So we have electron neutrinos. That's not really good. So rediscover the tau. Great. All right, we're good. Let's take this thing away. All right, so we have electron neutrinos that interact with matter to produce electrons, antineutrinos that interact with matter to produce anti-electrons, positrons. Muon neutrinos interact with matter to produce muons, muon antineutrinos produce antimuons, and so on for the test. So we have these 6 particles that all do different things. They're all, as far as we can tell, they have 0 mass, and they're all electrically neutral. We have those new guys, plus all of our normal matter, atoms. We have nuclei made of protons and neutrons. We have electrons flying around. We learn along the way, the whole lecture of its own, that there's substructure of the protons and neutrons, that they're at the smaller level made of quarks. These are the smallest bits of nuclear matter that we know about. Plus, these quarks have their own antimatter counterparts. There's all this other stuff that we found. These pions, and so on, all this stuff coming from space. And we have a whole bunch of rules now of how all these things interact, what decays into what happens when this runs into matter, and so on. So, for some perspective here, we're taking a long history. We start with the origins of science with like ancient Greeks through the 1600s or so, when we have basically 4 fundamental particles, or 4 natural elements, earth, water, wind, and fire, out of which everything is supposedly constructed. With the development of chemistry, starting really like this late 1600s through the 1700s, people begin to see that you can isolate different elements out of this, like iron and copper are very different things. And so people continue to discover things through the development of chemistry, and this sort of culminates around 1869 with the development of the periodic table of the elements, which takes all these known elements and categorizes them into a sensible way based on their chemical properties. And so we have this big table where these are now the fundamental particles out of which you can build anything else. And so for a long time we have, this is the number of quote-unquote fundamental particles as time goes on. So we now have around 100 Lego blocks out of which the whole universe is supposed to be built. So this gets greatly simplified in the early 1900s with the discovery that atoms are composed of a nucleus and electrons orbiting. Right? So now we have protons and neutrons in the nucleus and electrons flying out of them, or flying around. And you can use those little building blocks to build up anything you want in the periodic table. So now we don't have 100 fundamental particles, we have 3. Which seems like a much better place. We want nature to be simple. 100 seems really arbitrary. Then, through the middle of the 20th century, we have these cosmic ray experiments. They're discovering all of these new things, these pions and whatnot. And we know how they interact. We don't know what they're made of. They're not made of the same things as atomic nuclei are made out of. So we have just a proliferation of new particles and no real periodic table for them. It's so much worse than the periodic table. There's a whole book tabulating all these things. And so this, this just goes up forever until the discovery that we have quarks that are smaller than all these things. So you use quarks to build up protons and neutrons, and in fact, all these other things they found are just built up quarks in different ways. So here we go again from a huge number of fundamental particles down to something more sensible. And that brings us basically to the development of the standard model of particle physics around the 1970s, which is around where we are today. The standard model is a gigantic math equation. It's a mathematical model that collects together all of the known matter particles and encodes the ways that they interact with each other. Mathematically, it's a relativistic quantum field theory, meaning it takes into account both relativity of things traveling close to the speed of light and quantum physics that occurs on a very small scale. And it's all about groups of particles and how they interact and symmetries. When you think about symmetry in nature, you might think of something like a leaf or a snowflake, or if you're a nerd like me, you might think of the positions that electrons orbiting an atomic nucleus might take. And so I want to highlight what symmetry means in standard model. I think it's a very deep concept, which is beautifully outlined by this relation known as Noether's theorem that was put together by Noether in 1918. And what Noether's theorem does is it takes the fundamental conserved quantities like energy conservation and relates them to symmetries. So for example, in the standard model, the fact that physics is the same across all times, that if I do an experiment today and I do it next week, I do it 100 years from now, I should get the same answer. Noether's theorem relates that in a very deep way to the conservation of energy. Similarly, translation invariance, meaning if I do an experiment here, I do it over there, and I do it across the universe, I should get the same answer. That is now deeply related to momentum conservation. And so through Noether's theorem, the fact that nature is symmetric about space and time and other dimensions, right, is really symmetries that underpin the standard model, and through Noether's theorem are related to these deep tenets of physics, these conserved quantities. I would like to introduce the players of the standard model, the most fundamental particles as we understand them today. So let's our particle menagerie. So let's start out with quarks. We know about 6 kinds of quarks, which are called up, down, charm, strange, top, and bottom. They had some sillier names in the 70s when they were being invented. People called them up, down, charm, strange, truth, and beauty. I guess we got more serious out of it. So these quarks organize into particles called hadrons, which come in 2 types. There are mesons, which means middleweight particles, which are a quark antiquark as a bound state. So we take a quark and antiquark together, and you have a meson. And so the pions we discover are actually mesons. It's an up quark and a down antiquark. So we have 6 of these plus their antiparticles, 12 quarks total. Baryons are a little bit more familiar. So this is a quark triplet. And for example, a proton and neutron are baryons. Proton is 2 ups and a down, neutron is 2 downs and an up. So you can combine these things in a lot of ways to get a lot of particles, and since it's a bound state, you can, kind of like an atom, put it to different energy levels and get to like an infinite number of what appears to be different particles. And so that's what was going on, in the middle of the century of these cosmic ray things. It's all stuff that's really made out of quarks. Next we have the leptons, the light particles. And these are our electron, muon, and tau. Where the muon and tau is like a really heavy electron, and their corresponding neutrinos. Each one gets its own. Plus we have their 6 antiparticles: positron, the anti-muon, the anti-tau, and the anti-neutrinos that go with them. Finally, that column on the right deals with forces and interactions. So in the standard model, this is how the fundamental forces work. We have these matter particles, quarks and leptons, and the way that they interact is by exchanging some other particles that are messengers, that are called bosons. So I have an example here of 2 electrons that are kind of flying past each other and exchanging a boson called photon. This is the same photon that we know from light. Is the messenger of the electromagnetic interaction. So if you have two like charges that want to repel each other, or two opposite charges that want to attract. At the particle physics level, we understand that as they're exchanging photons. And in fact, all of the sort of everyday forces that we experience, like if you push against a wall, it's just an electromagnetic interaction. It's electrons in the wall and electrons in the so really, everyday forces are basically all electromagnetic gravity outside of like nuclear reactors. There's a few more fundamental forces in the standard model. Next on the list, we have the strong nuclear force. So within an atomic nucleus, you have a bunch of positively charged protons. And since like charges want to repel, the thing should go flying apart. But there is a uncreatively named stronger force that binds it together. And we understand this through, again, the exchange of one of these bosons, which is known as the gluon. So it like glues the nucleus together. So the protons and neutrons inside a nucleus are pushing each other apart, or the protons are pushing each other apart electromagnetically, but the gluons are binding them together. Then we have the so-called weak nuclear force. And this is what's responsible for all these neutrino interactions. So we have two new bosons called the W, which come in a positively and negatively charged variety, and the Z. And these are of special interest to neutrino physicists because the neutrinos would participate, so the leptons participate in electromagnetic and weak interactions. But the neutrinos are electrically neutral, so they don't interact electromagnetically. So basically, the only way they interact is through these guys. Finally, we have the now very famous Higgs boson. Last spring, the entire lecture series was about the Higgs boson. So there's a lot to unpack there. But just in very broad terms, we understand the masses that all these particles have as coming from interactions with Higgs bosons. Right, so the particles are sort of categorized in terms of which of these interactions they participate in. The quarks feel it all. They are charged, so they interact electromagnetically. They have a strong force which binds nuclei together. They undergo weak interactions with these W and Z bosons, and they have mass through the Higgs. The leptons don't feel the strong force, so they get the other three. But the electrons, being electromagnetic or electrically neutral, don't have any electrical charge. So they don't feel the electromagnetic force. It's only the weak interactions for the nucleus. That sort of brings us full circle to 1930 and beta decay. So if you recall, this was Fermi's theory, that we have a neutron coming in from a nucleus, and at a single point in space-time, proton, electron, and antineutrino come flying out. The way that we understand things today is slightly different. This is our modern perspective of beta decay, where we now know that the neutron is actually a composite particle. It's made of two downs and an up quark. And so when this decay happens, we have two of those quarks that are just spectators. They just go along for the ride and end up as part of a proton. The down quark spits out a W boson, which flips it into an up-type quark. So now we have a proton here. And a W boson goes off and decays into an electron and an electron antineutrino. So I think it is cool to think that, that is happening every time one of these clicks. So that is where we are today. Let's look at what we've done. So we start out, 1910s, 1920s, all this confusion about nuclear beta decays. Energy's gone missing, maybe energy conservation is over. In the 1930s, we have Pauli's desperate remedy, this letter that comes, and soon after, Enrico Fermi works out the theory. 26 years go by before these things are detected by Kalman and Ryan seeing blip blip on their oscilloscope. In 1962, we have a second kind of neutrino that interacts with these newly discovered muon particles. And in 2000, yet another kind that interacts with these tau leptons. And in the midst of that, around the 1970s, we developed the standard model, which is sort of our, in a sense, our periodic table of the most fundamental particles that we know about, and it encodes their interactions through these symmetries. So, that brings us to the 90s or 2000s, which I would call the end of the beginning. All right, so you can think, like we had that moment in 1956, thinking that everything is okay. But, you know, okay, neutrinos, all right, we wanted 1, we got 6. I think we're good, everything's solved. But, you know, again, neutrinos, they don't let us off. All right, and so next week, we will delve a bit further into this idea of these neutrinos coming from the sun. So, in the 60s, people had learned a lot in recent years about nuclear physics. And so they had a model of all of the different fusion reactions that would happen in the sun. They would produce neutrinos. You would see those neutrinos on Earth. You could predict the rate at which you would expect neutrinos. Right? That's my tens of trillions number. So you can calculate that in the 60s. And so shortly after those calculations are done, Ray Davis, who you may remember as the anti-neutrino guy, turns his detector to look for these solar neutrinos, these neutrinos from the sun, the home-stake solar neutrino experiment. And what he finds is, here's his data in red relative to the theoretical prediction in green. He sees a huge discrepancy. It looks like neutrinos are disappearing. And we're just detecting about 1/3 as many neutrinos on Earth as the theory predicts. So you might say, okay, we don't know nuclear physics that well, or we don't understand the sun, and certainly people said that at the time, but this lecture series is about neutrino physics. So you may reasonably conclude that, in fact, neutrinos have way more tricks up their sleeve that we haven't understood yet, that solar neutrinos will help us understand. So I thank you for listening. So neutrinos and photons are both out there.
Could neutrinos account for a good percentage of cosmos?
So the question was whether neutrinos could account for dark matter, which is an excellent question. And for quite a while, people were really hoping that that would be the case. To people that aren't familiar, so the dark matter problem is apparently things like galaxies are surrounded by a whole bunch of matter that we can't see. So if you study how galaxies move or galaxy clusters move, it doesn't match up with the calculations given how much matter we know is there. So it looks like there's invisible. So for quite a while, people hoped that that could be neutrinos. But as we've had more detailed studies of dark matter, people have built simulations of how massive the universe evolves. It appears that neutrinos can't be responsible because they're relative, they move very quickly because they're so light. And so they would tend to not coalesce like a cloud of dark matter. They would tend to scatter out the matter more than bring it together. So the neutrinos would kind of disrupt the organization of matter into the galaxy.
What about the total mass of neutrinos calculated versus the mass of dark matter? Significant?
No, so neutrinos are very, they're essentially massless. They're effectively massless as far as we've come here. They're very light. So they do have some influence. We'll come back to neutrinos having mass later on. They do have some mass, but it's very small. So it's a very small effect on the evolution of organization. Any other questions? Yes?
I think you said the standard model can explain everything that happens somehow explained by the standard model. Do you think somehow is it connected to the? Do you think suspect it's connected to the expansion of the universe?
So I think we'll have to go beyond the standard model to help understand that. So I think like dark energy. So there's a problem that so I said the universe is expanding, but in fact it goes beyond that. The expansion of the universe appears to be accelerating. And you'd expect that we have a universe that's full of stuff. Gravitationally it should be attracted, and so the universe should kind of expand at a constant rate or slowing down. So we need some mechanism to sort of push the universe apart at a faster rate. And so nobody really has any solid ideas about what that might be. But certainly it would have to be outside the confines of the standard model. We got some work to do. The standard model is, it's in a sense, it's collecting what we know. So it has some predictive power in that the periodic table, when it was developed, had holes in it, and people could go and look for those elements. And so the standard model is sort of the same way. It gave the structure and had holes in it, and people could go and look for these things, which was great, but it doesn't really tell us why. Like why there's 3 different kinds of neutrinos, or why things have the masses that they do, or so there's a lot that it needs to be desired. So I think there's a general consensus that there's something bigger, and that we're only looking at a piece of it. That the standard model is part of some bigger theory that is yet to be discovered, that hopefully would include things like dark matter, potentially dark energy. Yeah.
My question is concerning dark matter. Is it expected that neutrinos will survive in black holes? I'm sorry, not dark matter. Black holes. And the second question is, I'm sorry, may we have copies of your slides?
Sure, yeah, so that's your first question. I'll answer the second question first. Yes, there's a link to my website on the EFI's Compton Lectures website, the slides we posted on. But let me answer your first question now. So it'll act basically like light. So nothing can escape from a black hole, including neutrinos. So if a neutrino is going for a black hole, just like anything else, it will be consumed by the black hole.
You proposed or showed quite a number of points where you have detectors.
Mm-hmm.
Are you going to go into the structure of some of these?
I will, yeah, as we go on. So I started with sort of
This was
the simplest case, but yeah, as we go on, we'll talk about next week's solar neutrinos. So we'll talk about different ways that people have constructed solar neutrino detectors and why it had to be that way, and similar for other topics.
All right, then let me throw another question at you. You're using chlorine-37,
Yeah.
right? Unfortunately, chlorine, the chemistry of that chlorine is the same as the chemistry of any other chlorine.
Mm-hmm.
And it is prone to forming free radicals, depending on the energy input. How was that avoided? I assume that the decay of that is not the same as to forming argon-37.
Yeah, so it was a very interesting experiment, and actually there was the same detector that was used for the solar neutrino thing.
Okay.
So we'll cover that a little bit. But you're expecting neutrinos to come in and turn chlorine into argon-37, which is unstable, but has a quite long half-life. So it takes a long time to decay. So you would let it sit there for a while, and then actually bubble through gas to try to collect up some of the argon, and send that out to a little counting device, and look for the half-life of the argon decay, which was like a handful of atoms out of this huge volume.
So the efficiency is fairly low.
Yes.
I see. Thank you.
So it's extremely difficult experiment, and so there were initially a lot of skepticism that we just really never what to expect. Maybe that's it, but
Thanks.
he convinced everyone. Yes.
So in a supernova, you make a lot of neutrinos.
Certainly.
And is it, they interact with matter in a very big way, right? And is it the same way with the inverse beta decay and so forth, or is there some other effect going on there?
No, it's quite similar. They're essentially the same as neutrinos coming out of beta states. You produce, in a supernova, you produce kind of all 6 types. And so I think perhaps 2 lectures from now, we'll talk about the one supernova that was actually seen live in neutrinos, which happened in 1987, as well as attempts to detect kind of all the past supernovas that have happened out there in the universe and made a bunch of neutrinos. We try to detect those ones that are left. But they're all essentially low energy, like similar energies to beta decays kind of neutrinos. We use the same kind of detectors.
You mentioned, okay, the neutrinos are not massless, but they have very little mass.
Right.
Roughly, how many neutrinos would like to make an electron?
So we don't know how light the lightest neutrino is, but it's so we only have sort of limits on how light they are. So we know sort of they can't be any heavier than this, but we don't actually know what the absolute scale is of neutrino masses. But it's no more than 100 to 1,000 times.
What about the electron volt weight of a neutrino, light neutrino?
Yeah, so something in the ballpark of 1,000 or something. An electron is the heaviest it can be. But we'll talk a whole lecture on neutrino mass and what we know and how we measure it. It's a very interesting topic.
Is that mass the rest mass, or is that the mass of the neutrino when it's moving?
Yeah, that'd be the rest mass.
It's the rest mass?
You've got a screen here on Homestake, you've got a banded gold mine at Homestake, about a mile deep.
Yeah.
What what does that allow you to filter out so you can carry on? Is it sound or temperature, or what's in the uniqueness of that deep gold?
Very good questions. A lot of neutrino experiments these days are now conducted deep underground, and it's largely to filter out those cosmic rays that are produced in the upper atmosphere. So things like muons that would, on the surface of the Earth, muons are coming down about like a rainstorm, and so that can both present backgrounds you can mistake a muon or something that it produces for a neutrino interaction. And so by going deep underground, the Earth sort of filters those out, since they'll interact somewhere in the Earth and not make it down a mile underground. So that's the main reason to do that.
Were there sensors in the Hubble telescope that detected neutrinos?
I don't think there's any, well, I don't believe there's any neutrino detectors on the Hubble telescope. Although you could maybe use the Hubble telescope to to look at the distribution of matter and look very directly about how neutrinos have influenced the universe. I don't think we do any direct detection of neutrinos. Yes?
Yeah, my question is about life on the universe. Is life an inevitable consequence of the interactions with matter?
Oh, I think it's a big question, which I think no one has the answer to exactly, but certainly the universe is very big, and so we have an existence proof that life is possible here, and so it seems unlikely in a way that this would be it. That we're that phenomenal.
So the universe should be full of life. Perhaps. I mean, potentially.
As far as we know, the universe is full of matter.
No, I mean, we have a president now that is defying our explanation.
Yeah, certainly, it's totally fine with the laws of physics. Anywhere.
They put all these neutrino detectors real deep on the line.
Yes.
I would have thought that the different kinds of radiation and beta radiation from the radioactive materials that you're now closer to would mess that experiment up, so to speak. Yeah, you shield that from cosmic rays and secondary particles, but what about natural radioactive decay of Earth's radioactive minerals?
Yeah, so there's certainly radioactive things in the Earth's crust, which it varies over space, but it's pretty uniformly distributed in the Earth. So you don't get so much worse by going deep.
Oh, it doesn't get that much worse.
But certainly the experiments, in addition to going deep, you still have to shield them somehow. So for example, the big blue detector I showed, this other detector, it has the volume that it's looking at with a bunch of photomultipliers around it, where you're looking for nuclear interactions. And then there's a whole second volume outside of that, where you look for things coming in from the sides. So with additional instrumentation and shielding, you can try to block out some of that. So it's always there, whether you're a mile underground or...
And that's interesting what you said, it doesn't get that much worse coming down a mile.
Yeah. Yeah. You win a lot by getting rid of the... Yes?
I'm still trying to explain the expansion of the universe here today in this room. Theoretically, all suns emit neutrinos. Do they travel in a straight line, and can they, some go forever if they don't interact with sun?
Essentially, yes. So there's solar neutrinos from every star that ever shined. There are neutrinos from every supernova that ever exploded. And there should be, like we have a bunch of photons left over from the Big Bang, we should also have a bunch of neutrinos left over from the Big Bang. And then there are efforts to detect all of those things, which have not yet been found. But we believe that getting close to seeing some of these, to seeing the history of the universe or the neutrinos. Does that answer your question?
Is there any good book on all this that you can recommend to us?
Yeah, so I'll put together a reading list, also on the website.
Have there been any detections that can be associated with the recent kilonova?
I think people have looked, but as far as I know, I don't think anybody's seen any detecting neutrinos from that. Nor from the recent binary star mergers seen by the LIGO experiment in gravity, where people look for neutrinos going from that too. Didn't see anything. So far, I'll talk about it later, we've seen one neutrino, or 20 neutrinos from one supernova back in 1987. So we're really looking for another.
So these events will not produce
Sorry?
these events that will not produce neutrinos or produce very few, or what is it?
So there's many different types of supernovas, and most of them will produce neutrinos. It's just that if you get so far away, even it produces a ridiculous number of neutrinos. But it's just a matter of distance.
Or the density.
That they're so far away that the likelihood of any number of neutrinos reaching the Earth is just negatively small. So it has to be within 10 or 100 kiloparsecs. Close enough to see the neutrinos, but not so close that it.
When you say to reach here, but that's not the point. They will reach here.
They would reach here.
But
Yeah,
they are
just,
very
they get emitted in all directions. And,
low density. Yeah.
We're at a tiny little dot to them.
Now, quick question. Are neutrinos traveling at the speed of light, essentially, or not?
Essentially.
Slightly less than?
Slightly less than.
Yeah. Okay.
Yeah, so people thought, and as far as I've covered in this lecture, that neutrinos have no mass at all and travel at the speed of light. For reasons we'll discuss next time, we now believe that they have a very small but non-zero mass, and so they can only go a little less.
The old non-zero problem, yeah.
The big difference between zero and non-zero.
So what is the process that gives the neutrino the heat to go that far?
Any kind of nuclear reaction, even in beta decay. So if the neutrinos that are coming out of my strontium-90 source, just because they're so light, are going almost to like 0.9999.
But the still is a force that kicks in.
Yeah. So in this case, it's coming from the weak interaction. So this W boson decays into the electron that we detect, and the neutrino. The neutrino takes a little bit of energy, and even a little bit of energy is enough to have it going to speed of light.
And there's absolutely no chance there's a fourth type of neutrino.
Oh, there may be. Just such great questions, I love it. So what we know is that the weak interaction, these WZ bosons, that interaction involves 3 dependent neutrinos that we have. We know there's exactly 3 of those. But if there are additional neutrinos that do not participate in the weak interaction, there could be more. And there are some experimental hints that there are more, and that would be a huge deal in this picture of the standard model, and so we are hard at work on sorting that out.
Is it possible that a neutrino emitted by a galaxy just at the edge of the observable universe here might actually slow down when it gets to our vicinity, and so it would be in a reference frame that would be substantially less than moving at the speed of light?
Yeah, so certainly the neutrinos get reduced in energy as you look out further and further. So just like the universe is stretching out, so it will stretch out photon wavelengths. So photons from far away will tend to look redder, redshift, and the neutrinos will do the same thing. So I don't know if that's to the level that, yeah, I think that that's true. That from the very oldest, from the very origins of the universe, the so-called relic neutrinos are expected to be non-relativistic. They'll be moving kind of slowly in our brain.
So do they think most of the neutrinos ever created, even for the Big Bang, is still out there?
Yeah, so they're certainly expected to be leftover neutrinos from the Big Bang, and they have about the same density as photons. So it's like a couple hundred, I don't know. Most of the neutrinos that we have here are coming from the sun. So neutrinos going through you at any moment are, the tens of trillions coming from the sun.
You kind of gave a pretty good hint about the neutrino annihilation.
Yeah.
Could you, like a brief, so they don't annihilate typically, or they move out of the local space fast enough that they don't annihilate?
Yes. Neutrinos could annihilate each other. But the probability of interaction for one neutrino is tiny, and the probability of 2 neutrinos interacting is kind of tiny squared. So you need a really, really high density of neutrinos in order to get 2 of them and close that together to annihilate, which is believed to happen, but it's never been directly observed. But in the explosion of supernova, it's actually believed that neutrino-on-neutrino interactions would
so then
matter.
When like the quantum foam thing, where you have the spontaneous creation of particle antiparticles, and the neutrinos rarely, if they rarely annihilate each other in those.
So that's another example. The universe at that point is so dense that you have neutrinos and antineutrinos annihilating each other all the time. At the very beginning. Yeah. Neutrinos everything everywhere.
So 2 neutrinos hit on, they would turn into a photon?
Yeah. Really hard to get to each other though.
That's what happened when I meet some friends of mine.
Yeah. If you can do that, you can also measure the mass of the
Relative to that, with the 2 neutrinos interacting, assuming that they do to form a photon, is the photon then a function of the energy of the neutrinos?
It would be, yeah. So it would be the total energy of the neutrinos. So it would be the whatever kinetic energy they have plus the mass of the neutrinos. Yes?
Are there some neutrinos from the origin of the universe? Are they out still traveling at the edge of the universe?
Yeah, so they should be sort of uniformly everywhere.
Moving out?
Every which way. Going every direction. So they're created, the universe has expanded since they were created, so they're sort of still like they were, just kind of spread out.
Light, are they affected by gravity on their path?
In the case that neutrinos have, well, they'll be affected by gravity in either case, just like light. And there's if they have mass, that changes a little bit too. But certainly they would be affected like light, so things like light rays getting bent around very massive objects. Neutrinos would do that too. Yes.
Curious, someone had asked earlier about whether you would detect the neutrinos from specific recent astronomical events, and you said that most of the neutrinos here come from the sun. How can you tell the difference between what can you do by the source? I'm not questioning that you can, I'm just curious how it's done.
In the case of, say, a supernova, the detectors I described, you can't tell which directions the thing came from. But there are detectors that you can. So given, we're friends with the astronomers who observed the supernovas and they tell us where they were. And then we can go back in our data and see whether there was some extra neutrinos coming from a particular direction.
And it will all appear at about the same time.
Yeah, within a few seconds or so.
So if you had 6 instead of 1.
Exactly, yeah. That's what we're looking for. And that's what we're seeing in this one supernova, 1987. There's a whole bunch of them.
You're talking about how neutrinos have existed since the Big Bang, and of course we've produced more since then. Do you think eventually we can measure the age of a neutrino?
I think you can never detect the age of any given neutrino. So if we detected these relevant neutrinos left over from the Big Bang, for example, we could tell sort of indirectly based on the fact that they are at very low energies, that they came from a particular time in the evolution of the universe.